In the previous part of the course, we focused on individual pieces of data. We talked about integers, floating point numbers, characters, Boolean-like states, enums, variables, constants, and configuration values. That gives us the vocabulary for describing one field. For example, an order ID may use an integer, and geographic coordinate may use a floating point number, and order status may use an enum. A customer node may use a vector array. Real software quickly moves beyond the individual fields. A DoorDash order contains a customer, a restaurant, several menu items, prices, discounts, and address, delivery status, timestamps, and some driver's location. Our question today is therefore larger. How does software combine individual values into objects that represent the real world? And once we create those objects, how does the computer actually store and process them? That second question brings us from software design into memory and CPU behavior. And that we are building the backend for a food delivery application. A price, a restaurant ID, a delivery status have types. Each decision matters, yet the customer experiences the order as one object. This means software needs another level of organization about basic data types. The distinction is useful. A data type describes the shape of one value. A data structure describes relationship among values. Once you understand that difference, arrays, structs, pointers, and nested objects start to feel connected instead of hearing a separate C-length topics. Consider a customer ordering lunch for Chipotle through a delivery app. The customer thinks, I order a burrito bowl. A product manager sees a transaction involving a customer, restaurant, menu items, payment, address, delivery, promotions, and status. A back-end engineer sees fields, enums, arrays, structures, references, validation rules, and state transitions. The CPU sees address, bytes, checklines, loads, stores, and alignment. These are different abstraction levels describing the same underlying event. This translation ability is one of the main skills I want you to develop. Programming becomes much easier when you can move between the layer and the machine layer. The original structure uses exactly this chain. The user sees an order, the product layer decomposes it into business objects. Engineers encode those objects, and the CPU automatically processes addresses, bytes, check, alignment, and loads. Also, a customer ordered one burger. Representing one menu item is straightforward. Now imagine an outbound order containing 20 menu items. Creating fields such as item 1, item 2, item 3, and continuing manually creates a very poor data model. The repeat values share the same logical type, so they belong in a collection. In C, the simplest collection of elements is an array, like this one. This declaration says that items contains 20 positions. Each position starts one struct menu item. The array organizes many objects of the same type. That distinction called arrays and structs solve different problems. Arrays organize homogeneous collection, while structs package heterogeneous fields into one object. An array has an important property. Element occupy contiguous memory. Imagine each menu item occupies 64 bytes. If the first item starts at an address 1000, the next one might start at 1064, followed by 1128 and 1192. The exact number is on the side of the structure. The important point is the pattern. Once the CPU knows where the array starts and how large each element is, it can calculate the address of any element. Conceptually, address of item I equals base address I times element size. That regularity makes arrays simple for the CPU to navigate. To understand why contiguous storage matters, we need a small piece of computer architecture. The CPU executes instructions extremely quickly. Main memory or RAM responds much more slowly relative to CPU speed. Modern computers use this gap through several levels of cache. L1 cache is very small and extremely fast. L2 is larger and somewhat slower. L3 is larger again. RAM sits away in memory when the processor provides its required data in cache. Execution flows efficiently. When it repeatedly waits for RAM, the processor spends more time waiting for data, so memory layout can affect execution speed even when the high-level algorithm looks identical. CPU usually works with memory in blocks rather than requesting one isolated byte at a time. A cache line size on modern processor is 64 bytes. Suppose the processor needs information located at one address. The hardware may bring an entire nearby block into cache. This creates an important advantage for arrays. When the program processes items, 0 nearby bytes belonging to items 1 may already arrive in cache. When the loop reaches next element, the required data has a good chance of being physically close to data that the processor already fetched. This phenomenon is called spatial locality. The original lecture connects continuous array storage direct with cache-line fetching and improves cache hit rates. Think about Amazon Fulfillment Center. A worker receives a picking task for 4 products. If all 4 products sit in neighboring shelf locations, the worker can collect them through a short route. Now imagine the first product is in LA, the second in LH, the third on another floor, and the fourth on the opposite side of the building. The products still exist. The worker can still retrieve them. The field management changes the cost of retrieval. Behave similarly. A CPU benefits when the next required value is close to the current value. This analog also explains why data structure design eventually becomes a hardware question. You may hear claims such as arrays are 10 times faster. Treat such numbers carefully. A particular benchmark may show a large difference. Another workload may show a smaller one. Performance depends on access pattern, structure size, cache hierarchy, processor architecture, compiler optimization, and the amount of the data. The useful lesson is therefore more general. Contiguous map tends to provide strong spatial locality. Strong locality tends to improve cache efficiency during sequential processing. This is an principle worth remembering. The lecture makes the same quantification. The performance ratio is workload dependent. Cache locality is the underlying reason worth learning. Already slow many things problems. Now we need to slow one complex thing problem. Consider restaurant menu item. Its identifier may be an integer. Its name is a text. Its price can be stored as an integer number of cents. Quantity is another integer-like value. Its category can use an enum. An image location may use a string. These fields have different types, yet together they describe one business object. This is where a structure becomes useful.